Well, let's start our lecture number 14. And we concluded all the subject matter of boundary value problems, specifically to electrostatics, but the tools that we developed can be employed in all the material that we are going to discuss from now on. Okay, we are in this lecture talk about electrical conduction, and we have this schedule for, the summary for today's class. We are going to talk, just briefly comments how materials are organized in different types of properties that can be inferred from the band structures in solids in general. We are interested in materials in which we have free carriers that can be that can flow through the material through the application of an electric field. In other words, we are interested in conductive materials. We're just briefly going to comment on qualitatively on band structures of solids. Then we are going to conceptualize what is electric current and current density. We're going to talk about Ohm's law, experimental law, and principle of conservation of charge. And we are going to talk also about energy exchange in when you have free carriers interacting with an electric field, gain and loss. And finally, you are going to outline how we address boundary value problems in conductive media. What are the quantities that can be used to obtain the behavior of transport of free free carriers in conductive medium. As a basic reference, we have this our ebook on chapter 4. We have the whole material that is discussed in this lecture, and also you can take a look if you want to look a little more detail on band structure. Okay, you can go to Kittel. That's the other way around, double T, Kittel, Introduction to Solid State Physics. It talks about different aspects of material media, and including electric conduction, and they have the band structure of solids. Introduction to Solid State Physics. We know very well that we have different. We can classify different materials relative to their transport properties. You know that when you have an isolated atom, we know from quantum theory that we have different discrete energy levels. If you make a plot of the energy levels versus interatomic separation, you have two atoms, you put them far away, then you can consider each one not interacting with the other one. So we have, discrete energy levels. As we approach these atoms, you have now the energy equation that governs, the operator equation that governs the system now has interaction between the particles. And you start to form, as you see, several discrete levels that start to each level splits and the other level splits into new levels. Then you start forming several discrete levels. and we start to form those things that resemble empty spaces, empty regions, right? And as they are very close to form a solid, then you are going to have several energy levels very closely spaced, forming an almost continuous range of allowed energy bands, like so. Those energy bands where you can have energy states occupied by the carriers, by the electrons in the solid, are separated by those empty regions. So no state can be occupied in this region here. You have those forbidden bands and allowed bands. And different types of materials, they have, you can classify them by looking at some basic bands. You can have multiple energy bands, but in a very simplified way, if you have the lower range of energies is called the valence band, and the upper range, that's called is the one that's vacant mostly. These are the occupied. Those orange and this gray are the vacant. So we can call the lowest energy levels the valence band, the upper the conduction band. If you have very energetic carriers, they can move on the application of an electric field. So if you have this distance very far away, you have a good insulator, right? And as we approach the bottom of the valence band, the top of the valence band and the bottom of the conduction band, if they start to get very close, just by thermal excitation, you can have some of the carriers reach the conduction band, and if they reach the conduction band, they are relatively free from the attraction of the main nucleus of the atoms, and they can move along the material. And finally, you have some overlapping in a conductor. So this one, we have a small energy gap. We have what is called a semiconductor or semi-metal, or a semiconductor, right? And then you have a conductor. When the bottom of the conduction band overlaps the top part of the valence band. Obviously, this is just those squares. These are just diagrams. They don't represent anything. In fact, what you have to have is a diagram which is energy versus wave number of the wave function associated to the electron. So you have those things that might start at a minimum. Is zero, so we have energy in different valence bands. You might have, things like this. So you have, if you look at here, you have an overlap. You have two branches in this diagram, in this dispersion diagram, and if you have a given energy, you have one state in the conduction band, and at the same energy, you could have the same state in the valence band. This is just generic, okay? This diagram I'm drawing here. So you can have, this type of overlap we show in the picture is something like that, okay? So we have the top of the valence band has a higher energy than the bottom of the conduction band, like this. The top and the bottom, so they are like that. But you have to look into the energy diagrams, energy versus momentum of the electrons. Okay, so we are interested in these materials that have the possibility of having free carriers in the solids. We could have for instance, you can have a conductors, right? Metals. Like metals. You can have transport Mostly in conductors have electrons moving around. You have also semiconductors, in which you have electrons in the conduction band and movement of electrons by hopping in through different atoms, which we call holes. Movement of electrons in the valence band and movement of electrons in the conduction band, movement of electrons in the valence band is called, those special electrons that are in the valence band are called holes. So you have electrons and holes. Okay, you can also have, let me just, I put a Brazilian accent here, I'm sorry about that, electrons, no accents, okay? And also you can have ionized gases. The things we are going to talk about can be used, the quantities that represent transport in conductive media can also represents what happens in an ionized gas. You have positive and negative ions, right? You can represent, you can use the current density we are going to derive in this lecture to represent the transport, to be a representative parameter of the transport in an ionized gas. So, even though we are talking about, traditional conductors and semiconductors that are used in electronics, for instance, but we also can consider, the electromagnetic interaction in an ionized gas. We can have the same, quantities that we're going to talk about. Let's conceptualize the important parameters that represent transport in conductive media. One of them is electric current, okay? If you consider a conductor having a cross-section sigma, we say that we have a flux of delta Q or dq over dt current, which is I, okay? This is called the electric current and is measured in coulomb per second, which is the SI definition of the ampere. That's a macroscopic equation. Current says only how much charge is a scalar quantity, just specifies how much charge flows through a cross section of the material. It doesn't, specify direction of a free carrier moving on the solid. Right? We need something more specific to have that information, and that is the current density, which we are going to conceptualize now. So the current density gives information, right, on the direction of current flux and its local density as well. To obtain the final model for the current density, let's start with a very simplified assumption in which you have all charge carriers have identical attributes, which is very unlikely, right? You have one electron, for instance, moving this way, the other moves that way, then it has a collision, it scatters to the other direction, so they don't have the same velocity, they don't have the same behavior. But we are going to start with that simplified assumption, then we change to the more realistic one. So let's say that Q is the charge of the carrier, U is the velocity, and N is the carrier density. So N is charge density is measured in a number of carriers per unit volume. So unit is L to the minus 3. Okay. So so we can look then at let's align one volume, very specifically drawn volume of the material, parallelepipedic volume, in which one of the sides, one edge is drawn aligned to the same direction of the velocity. The velocity is in this direction here. So when we do that drawing and we make a parallelepipedic volume like this, we have a parallelogram on this side here, right? So we have this direction. So it means that there's no carrying crossing like this. All carriers, the carriers that enter the left surface get out on the right surface. They don't get out on the walls, either top or bottom or left or right walls. But everything that enters on the back surface gets off on the on the right surface, right? So let's calculate the volume. The volume is h is the height. So it's the area of this parallelogram here, which is the height times the length, which is u delta t, right? That's the area of the parallelogram times, the volume of the parallelepipedic volume is, the parallelepiped is w times that. And you notice that h equals to L cosine theta, right? And notice theta is the angle between the velocity vector and the normal to the surface. So that's what we have there. So if we plug this in there, we're going to have delta T U W L cosine theta. The area by itself is W times L, is a rectangle, right? W times L, which is this length here. So the charge, if you know the density of carriers, you have the density of carriers times the charge of each carrier, let's say electron, all right, 9.1 times 10 to the minus 31 kilos times delta V. Then we have, we can calculate then the total charge that flows across the surface, which is going to be delta Q divided by delta T. If you make the ratio, you can identify that you have here U times the area. The area is W times L, right? So this is the area. So you see that delta sigma WL. So I have U delta sigma times cosine theta, which is U dot, the dot product between U and delta sigma. Okay? So that's a little amount of current that cross this area, right? And so the current is just delta DI, right? DI that corresponds to the D is a differential of the surface, okay? So we have a D here as well, right? The D here is matched to the D sigma. So the D sigma gives me a current DI. So I have a sigma, I have to sum all the current on the macroscopic area, right? So that's what we get if we assume that all the carriers have the same velocity. You obtain just this relationship that involves the dot product between U and delta sigma. Well, let's go to a more realistic assumption. You have, distinct carriers. You have groups of carriers, and you have, let's say, you have capital K groups. Let's label each group by the discrete variable K, small k, right? The kth group has associated with it a density which is nk. The charge can be the same. Then we see what happens if we modify the charge. And the velocity, all the carriers in that group have the same velocity. The group might be only one particle, only one carrier, okay? So you would have only one. But if you have several, then have several at the same velocity. Then you can, each group might be just one particle. That's okay. So if we calculate now, it will just sum, right? I have that for the kth group, the contribution of the current, which is a scalar parameter of the kth group, is equals to, as we derived before, the density of carriers of that group times the charge of that group times the velocity of the carriers of that group times dot product delta sigma, right? So then to calculate the total current, you just sum right? That's what we do. Or then you have di equals to, then you're going to have a q factored out summation of well, this is like this, nk uk dot delta sigma, right? Then you have to identify what is this. Well, just notice that what is the sum right? If we had to determine the average velocity of carriers, what would we do, right? What would we have to do? Let me move here. Well, I would say, well, if each group has nk carriers, and if the total density is n, right, each group contributes to the average velocity with a fraction, which is this nk over n, right, times uk. Then I would sum over the group, right, of the k groups to get an average velocity. I mean, the weight is nk over n. N is the total density of carriers, right? Oh, that's what we'd get. So, in other words, the summation, or the sum, nk times uk, is simply n, which is the total density, which is something more tangible to evaluate, right? You have at a given temperature, you know approximately how many free carriers per unit volume you have in a solid. So this one is more tangible, more measurable than this one that is individual. We have to know the distributions in different groups. It's very complicated. So that would be n times v. V is the average velocity, which is another parameter that can be determined, using statistical mechanics. Those things can be determined. Given the temperature, given the type of solid, given certain microscopic parameters, you know what's the average velocity in a material. Okay, so that's what we have. So the sum is given by this, right? And then it means that di equals to q n v dot the sigma. This, if you look at qn, this is simply the, well, you can leave it as this, right? But you see that it's charge density, right? Free carrier density. Okay. So we define this parameter here, which is a macroscopic parameter proportional to the density, local density, proportional to the local average velocity. Call this the current density. Okay, so current density simply Qn times V for a discrete set of carriers. So let's just look at the dimension here. This L to the minus 3, this is L T to the minus 1, this is Coulomb, right? So we're going to have ampere per square meter. So it's a type of flux density vector, current per unit area. So if you have a continuous distribution, then if you have a continuous distribution, your density is simply the continuous charge density times average velocity. Well, if you can define those parameters, this is valid for any material. You can define a current density for any solid, liquid, or gas, right? If you look at this geometric construction, you have a solid with a cross-section, macroscopic cross-section sigma. Then we can calculate the currents if you know the density distribution, the current density. Well, just pick the contribution across the sigma, which is J the sigma. You just sum over the cross-section, so it means that you integrate on the current density function across the surface. That's the way you get the current, okay? For example, suppose you have a cylindrical conductor in which the current density is always constant, not constant, is always a point, is a constant direction, but it's variable, okay? If you look at this expression, the density is 0 on the z-axis, and the density is maximal at R equals A. So let's calculate the current that crosses this cross-section. So we just go, density is given by J0 R over A, AZ. In this case, it's simple, right? The sigma is in cylindrical coordinates, is R dr d phi, AZ. So you have J the sigma, the integrand of the expression, over A R square dr d phi. Then you have AZ dot AZ, which equals to 1, right? So we can erase this thing here. Then we integrate, right? The current is going to be integral from 0 to 2 pi of the phi integral from 0 to a of the remaining parts. We have 2 pi here, have r cubed divided by 3, j0 over a, I cubed over 3, and this gives a total current of 2 pi over 3 j0 a square, which is amps, right? That's what we get. Also, before we move to additional topics here, let's look at the special situation in which you have your volume is almost a surface, right? Very close to a surface. You can neglect the depth in the material, like a foil, like a sheet of material like this, in which you have a thickness T. Okay. So if you look at the cross section, which is drawn here in blue, you have the normal to the cross section. So the area is dl times T times the normal, the sigma, right? So the sigma here is simply T, which is constant, dl times n. So when you make the dot product between J and the sigma, so you're going to have J times T. So if you make in the limit T going to 0, you can define a surface current density, K, and you don't have to integrate across the depth of the sheet, right? You just absorb that T into the definition of the current density. Then you have the current that flows in this across the blue cross section is going to be J the sigma. JT you define in the limit as T goes to 0. You define as a surface current density in amperes per meter. So you're going to have K dot N. N is the normal to the path, okay? N is the reversal that's normal to the path that's being crossed. So that's how you calculate. I mean, the current for a current sheet, for a current over a surface, distributed over a surface, is simply calculated by the surface current density dot product with the normal to the segment that's being crossed, to the line segment. It's a line integral, okay, along the path that defines the cross section of the material. Okay. Just look at this example here. You see, given K, let's say this is a sphere, you have a surface current. We are going to get to a situation that that gives this type of current density. Okay, when you talk about magnetized materials, when you have a magnetized sphere, it has a current density on the surface that's given by this expression. K0 sine theta a phi. So we have a current distribution which is circumferential across the sphere, is along a phi, and change with the angle theta. So it's theta equals 0. There's no current here in the North Pole. Maximum current in the equator, and South Pole current goes to 0 again. So it's a variable current density on the surface. We want to calculate the current that across any path that goes from South Pole to North Pole, right? Well, by charge conservation, something we're going to talk about later, the current that crosses this segment is the same that crosses this other segment, which is a semi-circumference. So we can calculate through that semi-circumference. So you see that, looking in more detail here, this is the dl equals to a d theta, and the normal to the segment is this a phi. Okay? So dl a phi is what appears in the integrand. N is equals to a phi, and dl equals to a d phi. Sorry, d phi. A d theta, right? A d theta. We are talking about the polar angle here, so it's a d theta, okay? So that's what we have. That's the L. So if we calculate to have a simple integral, right? I equals to integral from 0 to pi k0 sine theta a phi, dot product with the normal, which is a phi, and the L is a d theta. You have an A here, right? So here we have A in meters, K0 ampere per meters, so we have amps. So I equals to, and this is going to be cosine minus cosine, so I'm going to invert the limits. So this gives 2, right? 2a k0 in this example. Okay? That's the result right here. Okay, let's look now. We have the current density concept. The concept has been defined. Let's look at free carriers under an electric field. Let's assume that we have in the real situation, what happens, we have in a solid, for instance, you have several types of interaction, but just for simplicity, put solid here, okay? Let's say an ionic crystal with nuclei that are all positive because we liberate electrons. When the electron moves along the solid, whatever is the initial direction, okay, let's say an electron is moving like this, is going to be, this ion is close to this electron, this is farther, so it's going to be pulled toward this ion here. So it's going to be doing something like this. Then it's going to be pulled across the other one, so it's going to be doing like this. So we have something, it's almost as if you had, collisions. You can model the thing as if you have, it moves straight. You can make a very simplified assumption. This thing is very complicated. But you can assume that typically you have a collision length, okay? Mean free path, L. So typically in a solid, the carriers are going to be moving back and forth like this, right? And you have a collision length, LC. This mean free path that the carrier has between collisions, when you have a significant modification in direction, is the mean collision time, tau c. So if you assume that initially the average velocity is different than 0, okay, let's assume that. We expect that because this different carriers moving into different directions. They have different collisions, so they move in. The vector sum of all the events after a certain time is going to go to 0. So after a very long time, you expect the average velocity to go to 0. If typically the collision time is tau c, we expect this process to take place naturally. When we talk about naturally, we are talking about a natural exponential decay. Many particles, right? So the vector sum of velocities, which gives the average velocity, goes smoothly down to 0 in an exponential way. If we know the collision time, we have an estimate on how this thing happens. It's going to happen exponentially decaying, right? If you look at this equation, this is solution of this differential equation, a first order differential equation, and that's what would happen without the application of an external field, right? We have this type of differential equation. Suppose now that we have let's look. Let's look at the meaning of this equation that we just derived by natural principle. Okay, this equation here. Let's assume we have a volume delta V of the material, and in this volume we have a total mass delta M and total charge delta Q. If I know the density, I know these quantities by knowing the number density of carriers. If we have the vector position x and have a small displacement dx, then you can relate the average velocity, rate of change of velocity, which is acceleration, the second derivative of position vector. So it means that v equals dx dt, right? So, so the equation that we just derived means that dv dt, which is the acceleration, is the second derivative of position vector, equals to minus 1 over tau c times v. If I multiply by the mass, I obtain a Newton's law, right? Mass of the volume times acceleration is proportional to velocity and opposite sign. That's Newton's second law applied to the delta V. It means that in the absence of a field, we have a force which is the type frictional type force. Every force that's proportional to velocity is a friction force, which is a lossy force. Irreversible energy is exchanged in this process. The energy is lost and you don't get it back. Okay? And now is always in opposition to the movement, to the acceleration. Now, if we include the application of external fields, we just have to add an extra force to the system, to the right-hand side. We have frictional force plus applied force due to an E field. The applied force is the charge times the field, right? So the new equation is going to be mass times acceleration equals to the frictional force. I forgot here the vector here, right? Plus the external force. Okay. So if we play around with this equation, you obtain now equation of motion that we call, right? Derivative of velocity plus velocity divided by tau c equals to q over m. How did we get that? Well, we had something like this, right? Let me just show you quickly here. We have something like this. Mass acceleration, which is dv dt, equals to minus mass over collision times v plus delta q times e. Then I divide by delta m, we have dv dt Then I move this over there, plus 1 over tau c times v equals to delta q divided by delta m times e. Well, if each carrier has charge q and mass m, delta q equals to the density of carriers times the charge of each carrier, right? And delta m equals to density of carriers times the mass of each carrier. So the ratio equals to q over m. That's why we get that relation there, q over m times e. Okay, so the equation of motion of the system of free carriers that suffer collisions with a typical collision time tau c under the action of an electric field is given by this expression. And we can solve, we have here 3 differential equations. We can solve for each one, okay? And you can then solve each equation. Let's say, just show it quickly here. We have something like this, right? dv dt plus q over tau c times v equals q over m times e. So in the ith direction, let's make it in rectangular coordinates. You have a simple equation like this. Right? This is a well-known equation. There's a particular solution plus the homogeneous solution we just derived. So Vi equals to Vi 0 exponential minus t over tau c plus the particular solution is when this derivative goes to 0, right? In other words, I can write like this, better. A plus b exponential minus t over tau c, right? So then we go at t equals 0, and at t very large, when everything doesn't change anymore. T equals 0, Vi equals to A, which is Vi at t equals 0. So this is Vi at t equals 0 plus a constant. So as t goes to infinity, this term goes away, the velocity goes, I'm sorry, I think I made a mistake here. Sorry about that. This is wrong, okay? So let me repeat here. Forget that. This is wrong too. Everything is wrong. I'll just erase the whole thing. Well, at t equals 0, I just get carried away. T equals 0, A plus B equals to Vi of 0. And as t goes to infinity, this term goes to 0. You have A equals to, when the derivative equals 0, right? So you have Q over tau c times A equals Q over M times EI. So A equals to, is this right? Oh, there's no Q here, sorry. This is 1. There's a 1 here. So we don't have this 1, 2. So A is going to be Q tau c over M EI. So that's the solution, right? A is calculated. B equals Vi of 0 minus A times exponential minus t over tau c. Then over here means that the velocity equals to, I can leave it like this, right? I can put something like that. See how did I write here? Yeah, I can put the steady state separate. Yeah, exactly how I did it. So the solution is like this. Is Vi at t equals 0, sorry, steady states plus so that's the any component. If you recompose, you can have the same thing, a vector. You can transform that into a vector, right? You sum each component, you have a vector. The solution is going to be something very similar to this one. V vector equals, you just remove the I, put the vector instead, right? V0 you don't have a vector solution, right? Which is the solution we got in our class notes. So, I mean, if you have initial velocity equals to V0, that's the general solution of this differential equation. In fact, I mean, if I have a solid that's standing by, we expect that the average velocity be simply equals to 0 at thermal equilibrium, right? Unless you have a superconductor in which you have a current flowing all the time at low temperature, you have a simple solid, let's say, initial velocity equals 0, so the solution is something like this, okay? Before we talk about that, let me explore this solution here, okay? This is very interesting. I'm going to illustrate the situation here. It means that whatever is the velocity initially, at steady state, this term goes away, and the velocity becomes in the same direction of the applied field, going along the same or opposite direction, depends on the sign of Q. Okay. What this means? It means that whatever is the velocity, you have a huge velocity initially with 0. If we applied a small field in this direction, very tiny field, after enough time, the steady state velocity is going to be along the E field, right? Whatever is the initial condition, how large it is, whatever direction it is going to end up going to the same direction of the field. Okay? So this is called the drift, right? It means that movement in a solid, I mean, you have this collision, right? But I mean, this moving, if you have a field that is applied in this direction, this thing that is randomly scattering around is going to move, you know, is going to drift like this. That's how the movement is. Have a lot of collisions, right? But in the average, this thing keeps colliding, but going along the direction of the field. So that's why we have an average velocity. We have collisions, but in the average, the centroid of the group of carriers going to that direction. So, I mean, going back to the more realistic situation in which V0 equals 0, the solution is something like this. I mean, at all the times, the average velocity is collinear with the applied field. Let's forget the sign here. Same, you know, with the same positive charge here, you have the same direction. So here's the curve, right? So for T much larger than tau c, for all practical purposes, the velocity is going to be the steady state value, which is q tau c over m, right? And if we go to the formula for the current density, right? If you put the V here, we get a conductivity coefficient that relates current density and E field. The current density then is simply multiplying this parameter by this parameter here times the density. I'm sorry, n times q. N times q times this velocity, so we're going to have q squared. So the conductivity doesn't depend on the sign, right? Whatever is the sign, the conductivity of a material is given by this formula, which is very well known. Right? The higher the density of free carriers, the higher the conductivity. The longer the collision time, the higher the conductivity. Okay. Also, it talk about ions, right? You have very heavy ions which are participating in the transport in the gas, or in the ionized gas, or in a ionic solution, for instance. If you have very heavy ions, well, the higher the mass, the lower the conductivity. So light charges contribute to a larger portion of the conductivity. Okay. So for our effects, depends on this collision time. In practice, if you apply a field on a conductor, good conductor, you're going to have an idea of this collision time, how much it is. You can calculate, right? You can calculate by estimating the density, knowing the charge of each carrier and the mass. It's not very difficult. And the collision time, we can estimate by measuring conductivity of a solid. I can have an estimate of the collision time. Okay? If you have, for instance, a binary mix of ions in a gas or liquid, right? Or if you have electrons and holes in a semiconductor, if you go back to the derivation, you have two different groups. You can include this additional group to determine the density, the current density. And if you separate in two groups, one of the electrons, one of positive ions, or one of electrons, one of holes, you're going to have that the conductivity is the sum of each group contribution, right? So it's going to be something like this. The collision time associated to the positive ions or holes in a semiconductor, effective mass if you have in a semiconductor, then you have the contribution of the electrons or negative ions in a solution. We can always use this formula to determine in linear systems the conductivity. Okay. Well, in between 1824 and 1826, Georg Simon Ohm made several experiments to determine what was the relationship between current and applied battery, right? The battery was already being employed at that time. Alexander Volta had developed it, and people started to make experiments with the battery. And one such experiment was, not one, but several experiments were conducted by Georg Simon Ohm, in which he played with different conductors, different cross-sections, different materials, and different lengths, and he established what was the relation between applied voltage and flowing current in such conductors. He observed that the voltage was proportional to the current, and for this situation. This is called the electrical resistance, the Z parameter, the capital Z we are going to use in this course. And he showed that this was proportional to the length of the conductor and inversely proportional to the cross-section area. This kappa parameter is called the electrical resistivity. This quantity later was defined by the International System of Units. Resistance was defined in ohms, and resistivity in ohm meter. So we're just talking about Ohm's law because that's an experimental evidence of the microscopic relation we just derived, right? We just derived a relation here which specifies that the current density for these simple systems, linear systems, is collinear with the applied field and proportional. The magnitude is proportional, and the degree of proportionality is the conductivity. Ohm's experimental law allows us to arrive at the same result. Okay, so let's see what are the implications of Ohm's law. If we apply Ohm's law to a differential element, let's say that the length is delta L, lowercase delta, uppercase delta sigma is the area. Then for this uppercase delta, have an uppercase delta I flowing across the conductor. Phi A is the potential at input. Phi B, this is very small, okay, and the cross section is so tiny that the E field is aligned along the conductor. So we can use the scalar analysis here very simply. Potential difference, the drop, right? Voltage drop, phi A minus phi B, is the field that points from the upper to the lower potential, E, times the length, delta L, that's the relation we have. And the current is J delta sigma. So if we applied Ohm's law, we have the potential drop equals to the resistance times J delta sigma. Let's calculate separately here. So we have the potential drop equals to delta phi. No, not delta phi. Potential drop is phi A minus phi B equals to E delta L. And the current that is measured is J delta sigma. So Ohm's law is that tension, which is the voltage, which is E delta L, equals to the impedance times the current. Impedance is resistivity, length over area, and delta I is J times delta sigma. So we have that, right? Then we cancel out delta L. Then we have E equals to kappa J. That's the relation obtained from Ohm's experimental law. So, I mean, the microscopic model gives us J equals sigma E. Ohm's law gives us E equals kappa J. So it means the same result, right? These are the same things. So it means that E and J are proportional. And it means that kappa resistivity is simply 1 over the conductivity. That's a simple consequence. In other words, the microscopic model that we derived is the same as Ohm's law, which was obtained experimentally. Okay? So here is a table having showing some of the conductivity and resistivity values for some interesting metals, some noble metals, some non-noble metals as well, and the semiconductor here. So if we look at conductivity, the figures for good conductors are typically 10 to the 7, almost 10 to the 8. So the number in SI units, conductivity is measured in ohm meter to the minus 1, and resistivity in ohm meter, right? So we have to look at those things here, 10 to the 7. Aluminum has a conductivity which is 3.7. Copper is 5.8. Iron is 1. It's worse conductor than copper or aluminum. Gold is 4.4. Palladium is 10 to the 7 approx. Platinum as well is 10 to the 7 almost, right? Silver is 6 times 10 to the 7. And in opposition to those, silicon, which is a good insulator, is 10 to the 3rd. So conductivity is 4 orders of magnitude, almost 5 orders of magnitude smaller than good conductors. That's one remark, important remark. The other one is that the best one is copper, not gold. Okay, copper is better than gold, and silver is better than anybody else, right? Silver is the best conductor. But what we have here is that copper oxidizes and loses this. I mean, it doesn't get as good conductor after it oxidizes. It's going to lose some of his properties. And gold doesn't oxidize. And silver too. Silver is reacts with ozone and sulfur. So it tarnishes, gets black, and loses his properties too. So the best choice, in fact, would be gold because of that. Gold doesn't react. Platinum also, but platinum is not as good as gold, but also platinum doesn't react. Okay, so here you have this resistivity, typically for good conductors 10 to the minus 8, right? 10 to the minus 7 is iron, but let's look at the good ones. Typically, the resistivity of good conductors is 10 to the minus 8 ohm meter. Okay. So just exploring a little more here, we can have very interesting materials that have, they are good conductor in one direction, bad conductors in the other one, right? You have graphene materials, for instance. They can control the conductivity along the plane of almost a sheet of atoms, right? So you have just a two-dimensional, let's say, material. No conductivity here, but the conductivity across that direction. You can make those metamaterials in which you can control the conductivity. You can have conductive polymers in which have very good conductivity in one plane and bad conductivity in the other one. So we have those anisotropic materials. And for those, we can generalize, if they are linear materials, we can generalize our relation, which is valid for isotropic. For an anisotropic material, you just have now a matrix relation, a tensorial relation. Sigma now is a 3x3 tensor, or a 3x3 matrix. So let's make a quick estimate on how much is the collision time for a good conductor. Now that we have numbers for the conductivities, okay? So we can estimate things looking at the expression for the conductivity. Let's go back. Let's make a conductor. Conductor conductivity, always like this, is density. It's easy to remember the expression, right? The higher the density, the higher the conductivity. It doesn't depend on sign of the charge, so it has to be Q to the square. The longer the collision time, the better conductivity. The higher the mass, the worse the conductivity. Okay? So if we know the conductor, which is a macroscopic material, I can measure conductivity by using experimentally Ohm's law. I can determine the resistivity, then I determine the conductivity. If we consider the mass of each if you have electrons that move in a conductor, you know the mass, you know the charge, And the density you can estimate, you can, for instance, based on the distance between atoms in a, in a solid, which is typically 3 angstroms, approximately. Depends, 3, 4, 2.5, can make it 3, okay, is a good number. Then we know the density, you can assume that each atom releases one carrier. Then you have the density because you know the spacing between atoms. So you can determine the collision time. I have this example here. We assume A equals 3 angstroms. That gives me a density of, you can calculate the volume of a unit cell, right, in a crystal. Then you have the length, you have the density, which is approximately 10 to the 29. If you get a good conductor with 10 to the 7th, like iron, right, ohm meter, this is -1 here, right? It's raised to -1. Then you can calculate, collision time, m sigma divided by nq squared. Then you can calculate that. So you're going to get something like this, 10 to the -14 seconds. So for our effects, after 10 to the -14 seconds, the average velocity reached steady state, current density has reached steady state. Okay, now we are ready to arrive at the principle of charge conservation, which has an impact in one of the Maxwell's equations. We are going to explore this further in chapter 6. When we talk, not in chapter 6, but when we talk about Faraday's law and displacement currents and the Maxwell's equations. But for now, we have, let's assume we have a closed volume enclosed by a surface sigma. We have an element of area, the sigma. The current density is J, and the total charge in the volume is Q of T. Let's assume that things can change with time. The charge is crossing either outwards or inwards across the surface. And the current, the total current is I. So charge conservation implies that the total current that flows across the surface has to be balanced by a change in the total charge, right? If the current flow is positive, this integral, which is I, okay, this is the current that flows outwards the surface. If this current is positive, it means that the rate of change of Q is negative. So we have to have a minus sign here to balance the equation. The current that flows outwards is minus the rate of change of the enclosed charge. So that's the simple principle of conservation of charge, or principle of charge conservation. It says that the current that flows across the surface has to be balanced by the rate of change of charge inside of the surface. So if you relate the charge to the charge density, the Q equals to integral of rho dV, then we have the integral form of the principle of charge conservation. Okay. The differential form is, you have the integral form is simply this. There's a closed surface, the current that flows is I, the enclosed charge is Q, so the equation of the principle of charge conservation is I equals to minus dq dt. So it means that the flux of J equals minus d dt integral of rho dv, right? Then you can employ Gauss's theorem to derive a differential equation, right? Well, if we fix the volume, the only thing that varies with time is the charge density. So if only rho varies with time, so we have, you can the derivative in time just is applied directly to rho. And if I apply Gauss's theorem here, and if we make a volume goes to a differential volume, then we can easily show that we obtain this differential equation, the differential form, right, of the principle of charge conservation. Is also called the continuity equation. Okay, so divergence of J is balanced by rate of change of d rho dt. So there are some consequences of this, right? Let me just derive here. If you have, that's the equation, right? Principle of charge conservation. If I have a material that obeys Ohm's law, right? And if in the material you have a solid that has a conductivity sigma, permittivity epsilon, then as in addition, rho equals divergence of d. If we relate d with E, this is going to be divergence of epsilon E. So then we have the equation gives sigma divergence of E so this is epsilon divergence of E, right? So divergence of E equals to rho over epsilon. Okay, so from the continuity equation for the principle of charge conservation, sigma divergence equals minus ddt of rho, which is epsilon divergence of E. Or let's leave us like that, minus d rho dt. Okay, so divergence of E is rho over epsilon, so we have minus d rho dt equals to sigma over epsilon rho, which is this one thing here. Then we have a differential equation for rho, right? Or you can define a time constant, a relaxation time, equals epsilon over sigma. It's easy to observe that it has a dimension of time. So I have d rho dt plus 1 over tau r rho equals 0. So we just replaced epsilon over sigma, sigma over epsilon by 1 over tau r. You can notice that this corrects the dimension here, right? Rho divided by time, rho divided by time. Solution of this equation is rho equals to initial value, exponential minus t over tau r, okay? So this is called the relaxation time. So it means that any solid, any conductor, has a charge Q at t equals 0, right? So the charge distributes with a density rho 0. After some time, the density goes to 0. All the charge leaves the volume and migrates to the surface. So that's what happens. That's what conductive medium gives, right? That's the solution for the continuity equation. So the volume charge decays, and the charge excess migrates, it goes to the surface. Just to give you an idea how large are those numbers. If we have, let's say, typical permittivity equals to that of vacuum, 8.854 10 to minus 12, farad per meter. Good conductor, the relaxation time is 10 to the minus 18. So in practice, for a good conductor, all charge excess goes to the surface immediately, instantly, right? We can calculate, for instance, transient fields in a conducting sphere, for instance. Very simply, using Gauss's law, assume that we have a sphere in which at t equals 0, the charge is injected in the sphere and it is distributed uniformly with a density rho 0. We know the solution for rho as a function of time. If the density is rho 0, it means that the density is going to vary like this. So at all instants of time, the density originally is uniform. It remains uniform at every instant of time. Okay? So we have a very high symmetry problem in which the density is always independent of coordinates. It's decaying, and this is independent of coordinates. Okay? For instance, at t equals 0, the charge in the sphere is the volume times rho 0. Outside, the charge is constant, so part is going to remain the volume as time goes by, and part is going to remain on the surface, and then eventually all the charge goes to the surface. But the charge is always equal to Q. So outside, the flux density outside is Q divided by 4 pi r squared, r larger than A. Doesn't change with time. Outside, you have always a uniform distribution, either on the surface or on the volume. By Gauss's law, if you use Gauss's law, you have your conductor, then you have a Gaussian surface, a spherical surface. Let me improve that a little bit. I'm going to do like this. Then I'm going to make those concentric, something like that, and I'm going to make it, this kind of thing. Let me improve this here a little bit. Then if you use Gauss's law, this is the sphere. This is a Gaussian surface radius r. So we have, let's say, region 2 and region 1. So d times 4 pi r squared equals to q, which is the 4/3 of pi a squared rho 0. So d, let's call it 2, equals to rho 0 a3 divided by 3r squared. That's for r larger than A, right? The field outside equals to, let's say this is epsilon 0 here. So is d2 divided by epsilon 0. It's going to be rho 0 a cubed 3 epsilon 0 r squared. The field is radial, right? All the fields are radial. I'm not putting the vector form. Now, if you make a Gaussian surface inside, let me do this one. Maybe I can duplicate this one here. I have space. Copy and space here. Oops, it froze. I have to restart my application. I think I lost that drawing, very probably. Sometimes happens. I have to do it all over again. is it? Let's see. Yeah, that's what I was. Just copying this thing here. Copy. Paste. And I'm going to resize. Make it smaller. Very small. So I have a Gaussian surface now inside. Okay? So I have a Gaussian surface with a radius r, and I calculate the field inside, so it's going to be d1 times 4 pi r squared equals to the density at time t times the volume is 4/3 4 pi r cubed. So I have the field inside, d1 equals to rho of t r over 3, right? So it's going to be a transient field, rho 0 r over 3, exponential of minus t over tau r. Then we have the field inside, E field, divided by the permittivity. Let's assume the conductor has a permittivity epsilon 0 as well. So it's going to be rho 0 r over 3 epsilon 0. And the current density equals to sigma. And sigma comes multiplying here, but can come dividing in the denominator. So it's going to be rho 0 r over 3 epsilon 0 over sigma. You can do like this. And this is the relaxation time. So J1 equals rho 0 r divided by 3 tau r exponential minus t over tau r. So I have, those fields inside that are transient fields. The current density is a transient current density. You can calculate the current if you want, okay? You can calculate a number of things, okay? So that's the result we got. It's not here anymore. Let me find it. 14 drafts right there. So, and also, I mean, these are the things that we calculate, right? Just showed how to derive those things in vector form. And then I can calculate the surface charge density. I can use, for instance, the boundary condition at r equals a, not the boundary condition, the boundary condition for d. The normal d has a discontinuity equals to the surface charge density. So we calculate the d outside at r equals a, the inside at r equals a, and you get this result here. The surface charge density changes with time. At t equals 0, there is no charge on the surface. At t very large, this drops, this goes to 0. The charge density on the surface is going to be rho 0 a over 3. Okay. Well, you can also derive this surface density by looking at the, let me do it again here. You have a volume charge and you have a surface charge, and the sum is constant, right? Which is the charge initially established. So this is in the volume. This is going to be rho 0 exponential minus t over tau r times the volume. I'm sorry, times 4 pi a cubed. Surface charge density is density, surface charge density times the area. And this is, in the volume initially is rho 0 4/3 pi a cubed. Then you can determine, you can divide by 4 pi a square, right? going to be something like this. 4 pi cubed drops. So you have rho s equals to rho 0 a over 3. Then you have a 1 here minus this factor here. That's what we obtain, right? So principle of charge conservation or boundary conditions. You have to get the same results. One important topic that we have to talk about is when you have fields and free carriers, we have energy exchange. This energy can be given by the field to the carriers or can be given by the carriers to the field. In passive materials or in dissipative materials, energy is given from the field to the carriers. But in active media, in lasers, for instance, in free electron lasers, in oscillators, special oscillators, fields are given, energy is given from the carriers to the field. Okay. So let's see how this happens. And this is very important. This formula is very important to understand what we have to do to exchange energy from one to the other, from system to the other. We have a big volume of material. Let's say that you have the coexistence, you have applied field and current density, right? Have an interaction. You pick a small volume in the material, small delta V. So we have a differential, which is the delta relative to the volume, and we have a differential, which is the dx, related to the changing time. Small shifting time dt gives a displacement dx, right? So if we define WE, the energy in the volume, right? Delta WE, the differential energy in delta V, okay? At the same time, dWE, the energy increment in V, in the total volume, for a change dt, then we have that the differential in time of the energy in the volume, d of delta W, is the energy increment in delta V for a change dt. Okay? So it's a double differential. We have a macroscopic volume. You go to a differential volume, right? You have one differential. The other differential is a small increment in time. How much energy does that give? So if we do that, and we calculate by traditional mechanics, the increment in energy in the volume at a time dt is the work done by the field, f dx, and we make a time derivative due to a change in the location of the center of the volume, right? The volume is changing position, right? The center of the volume is changed by the x. So the rate of change can be calculated. So that means this is the energy in the volume at the rate which is the ddt of that energy, which is the power exchanged between field and carriers. We're not saying that power is being dissipated. We are saying the correct word is power exchange, energy exchange, at the rate delta PE, which is only due to the volume delta V. Okay? So dx dt is the velocity, right? So the power exchange in the volume is force times velocity, average velocity, right, of the volume. Average velocity of the carriers that are in the volume. So electric force is field times the charge in the volume, delta Q, which by itself is the density times the volume, delta Q. The V is the same here, and this is Z, And if you go here, rho V equals to current density. So it means that the power exchange in the differential volume is simply the volume times the dot product between J and E, and you have the total power exchanged, which is going to be JE dV. That's a simple formula, right? It means that power exchange is the dot product between J and E. And then we have very important consequences of this formula. If this integral is positive or negative, right? Let's say that J is mostly, dominantly, has a positive dot product across the volume, right? So it means that power is being given by the field to the carriers. So we have a passive medium. So field transfer energy to the charge carriers. On the other hand, if mostly the dot product between J and E is negative, then you have negative power flow. It means flows from carriers to the field. So I have an active medium, right? So the carriers transfer energy to the field. So when people want to make some gain of electromagnetic fields, they somehow artificially they bend the J so that J is in opposite direction to E. So we can have in a free accelerator, for instance, electrons moving at high speeds, interacting with the field, and they make the electron to oscillate out of phase with the field so that J and E are in opposite direction. So after a certain length, the field that enters comes out amplified. So we have a free electron laser. That's how it works, okay? And also other things you can envision, right? You can have a free electron laser operating on that artificial condition in which J and E are in opposite directions. So I have J dot E negative. I have the Clarkson tube, which is a oscillator, a microwave oscillator. Traveling wave tube, which is an amplifier that works on the same principle. Okay, so passive medium, JE mostly positive, dot product. Active medium or active media, JE mostly the dot negative. Very well. Well, let's conclude this lecture now by looking. You have some homework assignments that deal with solving boundary value problems in conductive media. We are going to outline to you how to solve it, but after you know the step-by-step, you can use the same tools that we developed for solving boundary value problems in electrostatics to solve for the conductive media. The objective in general is to determine, for instance, what is the electrical resistance of a given structure, right? And electrical resistance, at the end, you have to solve a boundary value problem. You have to, for a given potential drop across the structure, what's the current that flows across that volume? Then you have the ratio between those quantities is going to be the resistance, for instance. So we are going to talk about steady state condition, right? Don't have transients, nothing changes with time. Recall that the principle of charge conservation, we have a time varying charge density. That's going to be, we are going to revisit that principle in, when we talk about time varying fields. Right now we are going to particularize to steady state. In other words, everything reached equilibrium, so that's the problems we want to solve. Consider a medium that is linear, homogeneous, and isotropic, has a conductivity. That's all you need to solve the problem, right? So you have the potential given on the boundary of the volume, which is area sigma. So we are going to consider steady state. It means that divergent of J is the quantity we want to determine. It's not D, it's not E, it's J, okay? So we're not going to play with electric field or with the current density. But our main focus is to get to J, to find J, because finding J, I find the current. Our objective is to find the field J, the current density. So divergence of J equals 0, because continuity equation, or the principle of charge conservation, the rho dt equals 0, means the divergence of J equals 0. At the same time, for static fields, right, stationary fields, curl of E equals 0, but E equals J sigma, E equals to minus gradient of phi, okay? And if you let me just do separately here. You have divergence of J equals 0, curl of E equals 0. So it means that E equals to minus the gradient of a potential, right? But you have to write this equation in terms of J. So because E equals J sigma, so sigma J divided by sigma equals minus gradient of phi. So if you find the potential, you obtain J directly in the form minus sigma gradient of phi. If I plug this in here, what happens? Well, divergence of J equals 0, right? Means divergence of this term equals 0, or in other words, Laplacian of phi equals 0. So in conductive media, the potential function satisfies Laplace's equation. Not Poisson's equation, Laplace's equation. Right? It means that we don't have net charges in the volumes. Would be rho over epsilon, but rho equals 0, right? Because all the charge went to the surfaces. Or you have charge flowing between two electrodes, but the total charge is always 0. We are always at equilibrium. So we have to solve a boundary value problem for the potential that is governed by Laplace's equation. And from that one, once you obtain the Laplace, the potential, you obtain the current density. So our final quantity we want to determine is the current density. So the step-by-step is like this. We solve Laplace's equation for the potential for the given boundary condition, either Neumann or Dirichlet boundary value problem, right? Then we obtain the current density by this recipe here, minus sigma gradient of phi. Then we obtain the current flowing through the two different electrodes that might be present in the system by integrating across a cross-section. Then we have the resistance, because we have the boundary conditions give you the voltage drop, right? And current between electrodes, then you have the ratio, you have the resistance, Z. Okay? So, what are the boundary conditions that we use in different situations? I'm just oops. So we have two situations. For instance, sometimes we have two materials, different conductivities, right, attached to each other with a common contact surface, or you have one material inside of the other one. The boundary of one of them is the interface between materials, you know. So in those two situations, we always have the continuity of the potential, phi 1 equals phi 2. So you need another condition, right? Well, but what is the quantity we have is J. So what is the boundary condition for J, right? If you go to the principle of charge conservation, I'm going to derive the boundary condition in general, okay? That's what we have in integral form. If we make a small cylindric volume with a small height that goes to 0 and make in the limit process, we have done that before already, so it's going to be very easy. It's going to be discontinuity in J normal equals minus rate of change of the surface charge density. Okay, that's what we would get for a time varying situation. Okay, but if we are at steady state, if we have the rho dt equals 0, then it means that the normal component of J is continuous. That's the result we get. Okay, so when this goes to 0, J normal equals continuous. So that's the second boundary condition. One is continuity of the potential, right, at the contact surface. And at the same time, J normal 1 at sigma c equals J normal 2 at sigma c. But what is J normal? Well, J equals minus sigma gradient of phi. And J normal is minus sigma derivative of phi relative to the normal coordinates. The normal coordinate goes from 1 to 2, okay? So it means that you have sigma derivative of potential 1 at sigma c equals to sigma 2 derivative of potential 2 at sigma c. That's the second boundary condition, okay? So continuity of the potential and continuity of sigma derivative. Okay? So then we solve the problem. Once you solve it, then you have your whatever parameter you want to determine, because after you find the current distribution, you can have that. Okay. Just as an example, we have this spherical resistor. This thing doesn't want to cooperate. Okay. Have a spherical resistor. So it means that, let's say that we have an electrode, an inner electrode of radius A, and an outer shell of conductive material, a ground electrode, okay? Let's apply potential, a voltage V relative to the outer electrode. So what is the resistance of this region here between A and B, right? So this is a boundary value problem, Dirichlet type. Potential is V at R equals A, potential is 0 at R equals B. So solve potential Laplace equation, we did that before already, it's very simple. VAB divided by B minus A, 1 over R minus 1 over B. Obtain J equals minus sigma gradient. There's some missing things here. I'm going to complete it here, okay? Obtain J minus the gradient of phi. Well, gradient of phi is the derivative of 1 over R, is minus 1 over R squared, times minus 1. So it's going to be, let me just do it here, something happens here, right? So B minus A R squared. I don't know, sometimes when I transfer those things, Yeah, I don't know what this. Oh, I think this B minus R is here. It came here. That's where it is. Came. So next step is to obtain the current. I know the density, right? So the current is the integral of J times the. You can pick any intermediate. Yeah, it seems behaving very funny. Yeah. So you can pick any intermediate shell surface between A and B and calculate what radius equals R, because it cannot depend on the radius. Charge conservation again, right? So we calculate J times the area of the surface, which is a vector AR, right? So this R square here cancels that one, right? And we are going to have the current is going to be given by this expression here. Then you have V divided by I gives you the resistance, which can be written in this form: L divided by sigma average surface, where L equals to B minus A. Average surface 4 pi R average, not average, effective radius R square. The effective radius is the geometric mean between A and B. Okay, so that's what we have. That's what we obtain. So that summarizes what we wanted to talk about electric conduction. We have some, more complicated problems to be solved in the homework assignments, right? There we have some situations in which we have, for instance, a resistive paper in which make a hole. So the question is how the current distributes, right? You're going to solve that based on the potential that depends on two coordinates, right? You can make it, in fact, you can make it x and y. Potential depends on r and phi. So it's easy to solve, okay? But that gives a way of solving the problem. And also have a volumetric region in which has spherical void inside. That's another assignment I passed to you for you to solve. Okay? So we conclude this lecture, and I hope to see you next time. Till then, bye-bye.